So today we will be doing, so if you recall correctly, long time back, years ago, we were doing some sort of rounding. Okay. So we'll continue to do rounding maybe throughout the end of this course now. So, but if you remember correctly, so there was a very nice rounding algorithm that we had for bipartite matching. Okay. So what was this weighted bipartite matching is that we had an LP for this, we solved an LP for this, solved LP, and then we had this rotate and round. And what was the property of this rotate and round was that when we rotated and rounded, we started with an LP solution x, okay, and we went to some x star which was integral. And what is the property of this? That the LP of x star, the value of x star was greater than or equal to value of x. And because LP was integral, because LP provides a what do you call upper bound on opt, basically what we saw that the value of x star is equal to same as LP value, right? So basically what happened that when we rotated and rounded, there was no gap, right? There was no gap. You understand, right? So generally what happens that you start with this fractional solution. When you make it integral, there is some amount of gap when we go. For example, the example of vertex cover, right? So we had a fractional solution, and when we rounded up to an integral solution, we lost some amount of this thing, right? So we could only say, hey, it is minimizes this, you have rounded up to 2, so that gave us a factor 2 approximation. But when we this bipartite matching, we did not lose this, okay? So today what I plan to do is that we will see a much more generalization of this phenomena, and okay, so we will see this phenomena in much more general context, right? And we use this in gap, right? We also use this idea when we were deriving factor half approximation for general assignment problem, okay? So it has a terminology, it is called Pipage rounding, okay? So if you don't understand this class, it is still perfectly fine, okay? It's quite mathematical, okay? So there could be a lot of things that you may not have understanding of, or may not know these things very well. So it's okay if you don't understand every details of it, but it is more for your orientation towards some of the things. But when you will do some exercises on that, you will start to appreciate it much more, okay? So the topic of today's lecture is Pipage rounding, okay? It is one of the more advanced rounding methodology in approximation algorithm, which actually generalizes this phenomena that we have been talking about up until now. Okay. So so to do this, okay, so I will go back to one of my old problems like max coverage, okay, and show this rounding to you, okay. So what was the max coverage problem? If you recall, you have an universe, right, and you have some sets S1 to Sm, okay, and you have been given an integer k. Goal is to pick k sets such that their union is maximized, right? That is my goal. So I want to pick k sets from S1 to Sn such that their union is maximized, right? So what approximation algorithm did we solve for this?
1 minus 1 by 2.
So we saw this factor approximation algorithm for this 1 minus 1 by k to the power k, and this implies that as k tends to infinity, this tends to 1 minus 1 by a. Is that fine? So, this is the approximation we already saw in the class. Okay. Now, imagine yourself that a slightly different setting, that suppose every element, okay, every element is present in f sets, at most f sets. Okay. Suppose every element of my universe is present in at most f sets. Okay. So, if I wanted to do this max coverage on graph, let us see what happens. So, what is the max coverage on graph? What is a max coverage on graph? So, what I want to do max coverage on graph. So, given a graph GVE, okay, I want to find set X of vertex set such that number of edges incident on X is maximized, and of course, mod X is equal to k. That is my constraint. So, this is like max coverage on graphs, or this is also called max k vertex, max k vertex covered or something, or coverage, max k vertex coverage, whatever. Okay. So, how can I write this problem, model this problem as a max coverage problem? What will be my universe? What will be my sets?
Do we use some other is this an additional constant that every element is?
Wait, suppose we will get to that. There is no like given this, can you write it like this? This is also like this. All three are bad. Can I borrow one blue and can we ask this person to bring?
I have asked him, sir.
Ask him.
I asked Johnson.
Yeah.
He said he'll buy and give me.
One. It's
Black
like
also?
black, yeah, because only these are more visible. Rest are like not that. And these are the best pairs. Don't ask him to buy other company.
Hamlin only.
Yeah, because others were like very bad. Okay. So first, forget about this. We'll get to this, right? But how can I model my max coverage in graphs as normal max coverage? What is my universe? Right? What is my universe, and what are my set systems? Correct. So, Sanjay is saying that suppose universe is H set of G, okay, and my set systems S of V is set of edges incident on V. Okay, excellent. Now, suppose every element is present in at most F set. Is this of what is the F here? Is it unbounded, bounded? Is present in this particular system, set system, every element is present in how many sets?
Age is 2 sets.
Okay. So, in this case, F is 2, right. So, what I am going to give you now is that suppose every element is present in at most F sets, then we are going to give you an approximation of factor 1 minus 1 by F to the power F. Now, notice that for max coverage on graphs, what will this implies? This will imply an approximation algorithm with factor 1 minus 1 by 2 to the power 2, which is 3/4. Is that fine? Right. So, notice that as f tends to infinity, like unbounded, this will also tends to 1 minus 1 by a. So, in some sense it is slightly more refined version of my algorithm. Okay. So, this is my goal using this. So, we are going to do this max coverage problem, and we are going to do this max coverage problem using and going to give you, we are going to assume that suppose every element is present in F sets, then I am going to give you an algorithm with approximation ratio this. Is that clear to everybody? Okay. Okay. Okay, so that we are done with. Now let's try to write LP for this problem. Okay. So you notice that this is a very general problem. I mean, like, so for example, if we had 3, then what would have got? If equal to 3, we'll get 1 minus, what is 1 minus 1 by 3? And 2 by 3 square is?
4 by 9.
So what is 1 by 4 by 9? Is it correct? Yeah. So this is also will be larger than, no, but this is like, there is something wrong, no? Okay. So what is this? 1 minus half, 1 minus 1/3 to the power third, right? So what it will be? 8 by, which is 19 by 27. So this will be also, you will see, much better than 1 minus 1 by a. So for every fixed, you like go. Okay. Anyway, that was just, what are you saying? Universe is edge. What is vertex? What is family? What is SV? Set of edges incident on V. Please wait. Think for yourself. Correct. An edge can be present in many sets. Please think. What is the definition of SV? That are incident on? Okay. So now you tell me, an edge can be present in how many sets? Wait. Yes, tell me. What did you get? Yes, no. What did you get? Because an edge UV is present in SU as well as SV. Can it be present in SW, which is not an incident, not an endpoints of U and B? Okay. Okay, no problem. Okay, so let's try to write an LP formulation for this. So how will we write an LP for this, right? So what are we going to pick, right? We are going to pick these sets, right? But what are we trying to maximize? What are we trying to maximize? Number of elements that are covered. Okay. Okay. So now we'll worry about it a little bit later. So suppose xj indicates whether the set Sj is picked or not. Okay. Right. So this is what my xj indicates, whether the sum set j Sj are picked or not. Okay. And so one constraint is very obvious, is that if I do this, then the one constraint is summation of xj, j going from 1 to m is equal to k. k. I do not want to pick more than k sets. So this is my fixed constraint. Is that fine? Right? Given that goal is to pick k sets such that their union is maximized. So this tells us that you have picked up k sets. So given that xj indicates whether sj is picked or not, this constraint is fixed. Okay. But now, how do I know whether an element is picked or not? Like whether an element is in the union or not. This I don't know, right? There's no way by looking at this. So I also need another variable, okay, for every element. So now we have, say, zi I in n1 to n, like this represent. So for each element, okay, and what is the meaning of this? For each element, whether element I is covered or not. Okay. So I should be, no, it's universe. What do you mean universe is? Wait.
So set of universe is set of edges, right?
Edges?
Set of edges is the universe.
What?
He's talking about
Wait.
graph.
We are not talking about graphs anymore. No, we are just trying to write for this.
That is fine, sorry.
N elements. Okay. So Z. So now, if I told you for each element whether element I is covered or not, then my LP constraint is very this thing. I want to maximize what? What I want to maximize? Right? Z. This is very clear. But now, what is the relation between the sets you picked and the elements you have covered? I need some relation between them, right? So what is the relation between them, right? So if you want to pick I, you have to pick which set? Sets that contains I? Okay. At least one of the sets. Okay. So look at the sets. So now let's fix I, j in 1 to m. Okay. I belongs to Sj. Like for all I in 1 to n, look at all those sets that contains an element I, right? This tells us whether this summation tells us if it is 1, what does it mean? If this sum is 1, what does it mean? Definitely one of the sets that contains an element I has been picked. Is right? So then Zi should be less than equal to this. Right? Why? Because if an element is picked, Zi can anyway take 0 and 1, right? Then this is fine. But if Zi is not picked, then you can take anything here. You understand?
But why this inequality? Because if the
Imagine yourself,
because it can be covered in more than one.
yeah, it covered in 10 sets. So this guy will contribute 10, but like, yeah. But I also, when I don't get covered, right, it's 0, right? Yeah, right? Is this end of all my constraints, right? So now, of course, I have Zi is greater than equal to 0, xi is greater than equal to 0. That's it. This is my all the constraints that I want to write it. Okay. So notice that, wait, yeah. So optimal integral solution is going to be less than LP of u comma s, which is given by this, is right? So if I look at an integral optimum solution, so now let's see why this satisfy the, look at any integral solution for this, okay? I claim that all these constraints are satisfied. If I look at any integral solution, I tell you that all these constraints are satisfied, right? Of course, you have picked up exactly k sets, so this is equal to k, all right? Look at any element, this is either 0 and 1, right, and it is upper bounded by all the sets that had been assigned 0 and 1. So if you belong to one of these covered elements, then this is at most 1. Yes.
For the ILP formulation, xi zi was 0 1.
Correct.
When
So
you make it LP, then why it is not only greater equal to 0, why it is not
don't care. It automatically will be.
How?
I don't know. Like, why do I force any other constraint? Please tell me. Why should I force any other constraint?
Usually when we relax, like take 0, 1, we relax in a way that if greater equal to 0, less. It's the general.
When, no, who has told you this? What is the meaning of relaxation? Relaxation means that I allow you to take any rational function, any rational number. It automatically will become.
Why you are taking greater equal to 0 even? Negative portion is also comes.
No, this is my constraint, but I do not want to constrain it with at most 1. That's up to me. Like, will it, what goes wrong if I do not put any constraint that it is at most 1?
Okay, it's a max.
Wait. Imagine, like, I have even more bigger domain.
Yes.
Then maximization can be only bigger. So how does it matter?
So feasible LP space will be even bigger.
Huh? So fine.
Second, there is a problem. I mean, because it's a maximization problem. Suppose Zi is arbitrarily an infinitely large value.
This is unbounded.
The lower bound will not.
But
be a
then
problem.
what happens to this?
That dries up x also. The only constraining part is the equality. That the summation of the exercise can't be so big that that equality constraint has to be satisfied. That's the only thing that's restraining the value of x.
Okay.
That is the essential thing.
So you
Hmm?
mean it will automatically
Yeah, it will
fall
less
under
than-
Tell me.
Less than
all zeros for Zi is a peaceful solution when xi is greater than or equal to 0.
Okay.
So if I put Zi less than or equal to 1 alone,
Hmm.
then it means Zi is greater than or equal to 0 and less than or equal to 1.
So what's wrong in it?
When I put Zi greater than or equal to 0 alone, can Zi take the value of 2 or 3?
now it can.
Let it take.
But it is upper bounded by value of x.
Yeah, and that's driving the value of xj also.
Wait.
But the summation of the xj's must be at most k. So xj can't be unboundedly large.
Who told you that it cannot be unboundedly large?
Because the summation of xj equal to k. If zi, the value of zi.
Yeah.
is
So
five,
do I need at most 1 or?
No, that's. But I'm just trying to say that's part of the thing that constraining.
Why?
Because the number of sets that contain it. So say there is one element which is being taken by 5 sets.
Okay.
Then you take each of those 5 sets.
I took it.
The maximum of those will come to how much will be 5.
So, like, is this like why? I mean, I do not understand that why I need to constrain that this is at most 1. I mean, I can, but why? Give me a reason. Why should I do it? What is my objective LP relaxation? That I have my integral solution. I look at a domain where I can do something feasible, right? And that's it. Can any Jedi take more than k?
No, x.
Wait, Sushmita. Can any Jedi take value more than k? So it is at most k. So this integral in this is also bounded. But why do I care about bounded or unbounded? Have I told you anything? I might like to do it, but for a different reason. But it should be clear to why am I doing it. Like, if I put Jedi not equal to 1, can't I solve this LP? Is that your question? But anyway, you don't know how to solve LP. So what are the questions we are asking?
Also, if one element is common in every set.
That can happen even now.
Yeah,
Why? I mean, we are not finding disjoint sets. No, I do not, like, why, like, even if I put Jedi equal to 1, what do I get? Like, what constraints are you, like, what are you able to achieve because of that? Still, I can pick sets in which an element can appear in multiple sets. And it will. Imagine imagine an instance where one element is common to all the sets. Whatever I do, I will have one element which occurs in k sets. Look at a set system where an element appears in every set. It can happen, no? No. Then this is going to be k then. Whatever I do, this is going to be k. So I do not understand your question still. Like, what are you trying to comment?
Given an IT solution of this, can we come up with next coverage?
Given an
IP solution of this.
okay, given an IP solution, integral solution. So you have picked up some k sets, no? Fine.
But is this the maximum in this next coverage?
I don't know.
So what I say, it has to be only feasible. When you have an integral solution, it has to be feasible in the LP. It doesn't have to be.
Wait. No. With respect to, like, okay. It is a feasible solution. Huh? It is a feasible solution. Because what is a feasible solution? Just pick some k sets. That's all that is a feasible solution. Picking any k sets is a feasible solution. You understand? I don't know. This I don't know whether it is optimum or not optimum. Right? But I know whether I can get a solution or not, that's a different thing. But I know its value is not more than that. Right? Number of elements that can be covered is not more than that. That's all that I care. Okay? You understand? For example, in minimization problem, do we ever bothered? No. Okay? But we might like to constrain it for a different set of reasons, right? But like as such, there is nothing wrong in it, right? If I get a value here, whatever may be the value here, that is going to correspond to this, right? That is going to provide an upper bound on my optimum. That's all that at this point of time I care, right? So why are we putting certain mode constraints? There should be reason to put those constraints, right? For example, I might like to optimize over 3 points, 0, half and 1. That is also a relaxation, right? But that relaxation may be NP hard as much as 0, 1 is there, right? But that, look, just by looking at, look, if I allow a 0, 1, I allow a third point, that also a relaxation, because now whatever set of points you were, I have just increased enlarged any point. You could have 0, 1/4, half, 3/4 and 1. I can also optimize over those fixed relaxation. You understand? Right? Look at a vertex cover LP. Actually, it is an optimization over 0, half and 1. It doesn't need to use any rational coordinates. And the optimum with respect to any LP and 0, half, 1 is good enough. But sometimes I do not want power of LP. Maybe I want to do relax over 0, half and 1 because it is easier for me to round it then.
Yeah, that was my question. If in here, if the LP feasible space is too large because we are not upper bounding it, and the rounding.
Look at minimization problem for vertex cover. Like,
Can,
us.
so if the rounding algorithm is such that it gives an integral solution, I won't say solution, it gives an integral solution which takes more than one, like 2, 3, that is not even a feasible solution in ILP. So
What do you mean by feasible solution in ILP?
You mean to say that in ILP we are saying Z is 1 and 2.
So the
Sorry,
Y-
0 and 1.
The LP solution need not be a feasible solution for ILP. It's
Yes,
the
but
other
when
way
you
around.
round it,
Like what do you mean by rounding? But rounding is not a fixed procedure, no?
it's an algorithm.
Rounding is, I define those algorithms, no?
I see.
Is there a fixed God known algorithm for rounding?
No, for different problems.
You
Yes.
fix what
So
value you want.
rounding, my job is to find a feasible solution to my problem. That is the basic objective of my rounding. Is rounding just doesn't mean that, oh, it is 2/3, make it 2. It is less than 1/3. So like upper seal and lower seal. That's not rounding is always about.
So you make the rounding algorithm such a way that it falls within like just 0, 1.
That's
which
like,
takes
that's too much.
Also, rounding is not the only way to deal with, to interpret an LP solution in terms of approximate ILP.
I think we are just going in a very different tangent for no reason.
No, I mean just this point that rounding is one way of interpreting an LP solution in terms of an ILP solution. There
Of
can
my
be-
current problem.
Yeah, there can be many other processes. And what is the rounding threshold? That is depends on some other mathematics. It's not just half. The examples you have seen would be like the vertex cover is half, but there can be some other rounding scheme also.
Okay, I need to. Okay.
Okay, so the main takeaway message is an LP maximization problem, a solution will be an upper bound on the ILP maximization. And that's it. And as long as an ILP solution is a feasible solution for the LP, that's all we need. That's all the mathematics says.
Okay, let's go ahead. Otherwise, I will go nowhere in the class. Okay. Okay. I mean, I don't like to add any constraints to my LP till I don't need it. I constrain my LP only when I need it. Right? At this point of time, all I care about from this LP that if I solve this LP, I get a number. The number is an upper bound on my ILP. That's it. That's all that I care. And why? Because look at any integral solution of my this. That is a feasible solution to this. So if my domain of feasible solutions is much larger and that contains whatever points I am optimizing integrally, then I'm perfectly happy because it can only be larger, it cannot be smaller. Okay. 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 So okay. So now imagine this looks bit hairy LP. Okay, this looks like little bit hairy LP. Okay. Okay. So the reason which will become little bit clearer later, I would like to eliminate this variable Zi. Okay. What I want to do? Eliminate these variables Zi. How can I eliminate these variables Zi? Right. So what should I set? Right. So I want to eliminate these variables Zi, and there are several ways of eliminating. So what I will set is like it's so suppose you are given me these xi's. Okay. What can I set Zi that it will satisfy all this? So I could set Zi. Okay. I could set my Zi to be what? Minimum of whatever is minimum, for example, and it will always satisfy 1 comma summation j in m.
Why do you want to eliminate the ZX?
Because it will become clear little bit later. Like I am not an expert in this area that I can go that much far. Wait. So Zi what? No, that's not the reason. I mean there are just 2n variables, these things that matter in life. Like it is to understand few things much more clearly. So to eliminate this, I do the following thing. Okay, and this is where I've incorporated this one business, whatever I wanted. Okay, so you have to have a patience. 1 summation j in m, okay, I in sj xj. This is what I can set my Zi to be. Okay, minimum of these two quantity, whichever is minimum. If one is minimum, then I set this, right? Because all it tells me that whatever it is, this element is covered, right? Covered. Okay. So these two LPs are exactly the same, but if I wanted to do this, as all of you people are saying, hey, you make Zi to be at most 1, you can also make xi at most 1, and it wouldn't change anything. But there should be reason to do this. You understand? Why? Because even if I put this constraint, I am still solving, still whatever it is LP is, it is still good enough for my purposes. Right? For example, as I said to you that many times in parameterized complexity, we actually solve over 0, half, and 1. You understand? So we solve our LP over this, like this. It is hard, but in some cases we can solve it nicely, and then we can use those properties for my algorithm. Okay? But now, if I look, if I write like this, then what I can solve that my opt is less than equal to max of some function L of x, x in some polytope, or set of points where I am trying to optimize this function. So max covers, and what is L of x? Is nothing but, what is L of x? Right? I in u, right? What is this? I in u, okay? And this. 1 second. This is what I want to maximize. So I want to maximize function L of x over some domain. Okay? And what is my domain? What is my P? P is nothing but x in 0, 1 to the power m, and summation over j xj equal to k. Is that fine? So I am only optimizing myself this over these kind of points, right? So that LP and this LP are equivalent. That and this are equivalent. Okay. So what I want to optimize? I want to optimize this function L of x, which is for each element it takes minimum of this, this, right? And what is the polytope that on which I am trying to maximize this function? X in some 0, 1 to the power m. So this takes every point between 0 and 1, and but the summation of those coordinates should be equal to k. I am only worried about this polytope. Okay. If you look at this function L of x, it is not linear function. If you try to write this, it is not a linear function. You understand? Okay. What is this? This is a function from Rm to R, right? Because it takes these m points and outputs me this, right? So this, you can think of this L function is from R to the power m to R. Have you ever written this? How can you write a max of 2 points? It is never a linear function, right? Do you know how to write a max of 2 things as a function? Do you know how to write a max function? Doesn't matter. Okay, this is not a linear function.
So the objective function is not linear, but
This
the constraints are still linear.
Yeah, but we still don't know how to solve it, right? Okay, but this and this are same, and this we know how to solve it, right? So although this is not a linear function, I will just solve this, right, and give it to you.
Why then did I need that?
You will see in the please. Okay, is that fine?
So here the objective function is Lx.
This is my objective function, right? Opt is less than equal to max of L of x, x in the polytope, where L of x is this function and polytope is this.
This is constant, like p.
P is a constant, or like, yeah, it is a constant.
It's a space in which you are finding a solution.
Yeah. This is a feasible space, or yeah, not feasible space. This is a space. Feasible space is a very different word. Right. Yeah, actually this is a feasible space because I have already put xj equal to k. Okay, so this is what I'm trying to talk about. Is that fine?
Second,
Yes?
hello.
Yes, tell me, Pallavi.
So, in the previous LB, you are trying to replace ZI,
Hmm.
right?
Hmm.
So, we instead of ZI less than equal to summation constraint, we write ZI is equal to main constraint,
This constraint.
and everything has remained same.
Exactly. But since I replaced Zi with a min constraint, I went and changed my optimization function. Right? I replaced my optimization function Zi also with those things. Okay? Okay. It's a good exercise to write that if you want to write this as a function of x and this, you can show that this is not a linear function, not a linear function. Okay? So my optimization function is not linear, and hence we don't have an algorithm to solve it. But we know how to solve it because I will just solve it and give it to him. Is that understand my point? Is that correct? Is that okay, Pallavi?
Yeah, okay.
I'm not writing it to solve it. I'm writing it for comparing few things. Right? So I'm saying then it is easier for us, it will be easier for us to compare as we go along. Right? So I converted, by eliminating this, I converted into some other quadratic program and we did this. Okay? Now let me write another quadratic programming, okay, for the problem. Okay? Let me write another non-linear program for this object. Okay. Okay. So what is my another non-linear function for max coverage? So what I'm going to do, max coverage, this is a very beautifully this thing, and you will see this. So I'm defining my f of x as summation over I in u, right? I in u 1 minus product j in m, I in sj, xj. You understand? So this is what it is. Now notice if I write this, okay, for if an element, look, when will this function be 1? Right? So if you notice, wait, what? Wait, I'm talking about, suppose xj is in 0, 1. Okay? If xj is in 0, 1, then tell me what is the function value is. If an element appears in the set, how much is it going to contribute then? Okay, wait, Sushmita, wait, what I'm trying to do. Let me think about it for a minute. This is correct? No, I should not do this. This is what I want to write. Okay? Okay, so now what happens? Imagine yourself, if a set is picked, if a set is picked in which I is there, this term will become 0. It means that term will contribute 1. Right? But if some element is not picked in any set, then what will this term contribute to? 1. So 1 minus 1 is 0. Right? So this precisely counts number of elements that are covered by my k sets. Okay. But by no stretch of imagination this is a, right? Right? So I want to optimize this function with respect to the same set of constraints, right? Summation xj, j equal to 1 to m equal to k, and right? So this is what I want to constraint, and xj is between 0 and 1. Right? Is that correct? This is another formulation. No? I want to optimize this function to do this. So now I can write again opt is less than equal to max of f of x, x in the polytope. This is what I defined. Is that fine? So this is what I want to optimize. So my opt for max coverage is less than this object. Opt of my max coverage is less than this object. Okay. Amazing thing is this we know how to solve it, this we don't know how to solve it. look, this and this are same, but here is a quadratic function that I want to maximize. Meaning doesn't mean that I can optimize this particular function, right? Look, this optimization function, I can write it as a linear function. But this I cannot write it as any linear function.
Sorry, but you said L is not a linear.
This L is not a linear function, but this constraint can be converted into a linear program. So they are equal. Their optimization and their optimization is equal. But here I can't say this. You understand?
Are these two not equivalent?
What? No, they are not. They're
Not equivalent with that the fx is counting the same object.
doesn't matter. When I relax it, over which polytope this function is maximized, over which polytope that point, that is not clear. You understand what I'm saying? This, so I wrote, this is my LP. With the help of this LP and this say non-linear program 1. Okay? Non-linear program 1 is equal to LP. They are exactly the same object. Right? Because to solve this, I can literally convert it into LP and say, hey, it's, but non-linear program 2 is not equal to LP. This is all that I'm saying. Okay. So you can think of this as like, I have written like this so that it is easier for us to compare. But actually, this is a conversion of a linear program into a quadratic program. But here I started with a quadratic program, I don't know how to make it linear. Right? But here, if you give me this, I can write it a linear program and I can solve it. So there is a very basic difference between this nonlinear program and this nonlinear program. Okay? We don't know how to solve this, by the way. But we know how to round it amazingly. You understand it? So what we know, that this is like, if you give me a feasible solution to this program, if you give me a feasible solution to this program, I will round it to an integral solution with the same value, just like our bipartite graph. You understand my point? So what did we prove in the bipartite graph? If you give me a feasible solution to my bipartite matching LP instance, then I can round it to an integral solution of value at least this much. Similarly here, I don't know how to solve this, but by God's grace, if you give me, what I know here, if you give me a feasible solution, okay, a feasible solution, right here, I will give you an integral solution, okay, I will give you an integral solution of value at least same. So just like LP for bipartite graph, when I do rounding here, there is no loss. But I don't know how to start, how to find this point. So if I can find a starting point of my solution for this, which is not too bad, then I can at least convert that into a solution. Because once you give me a solution to this, I know how to do this rounding. And this is a rounding what is called Pipage rounding. Okay? So given a feasible solution to this continuous relaxation, this is called continuous relaxation. This is also has a name. I think it is called continuous relaxation. Yeah, or it is also called continuous coverage. Okay? This is like, these are not, I'm going completely out of my comfort zone. So this is what is used in different places in game theory and like all kind of things. We'll get there, but like I'm not in my comfort zone. So my knowledge about these things is just a week old, not more than that. Okay, but we'll get there. So yeah. Okay, so this is also called continuous coverage. So but I'm making a very larger point. Okay, so what is the larger point that I'm making? Okay, so now the larger point I'm making is that look. So let's write it down. Okay, let's write it down what I'm trying to communicate at this point of time. First, don't know how to solve NLP2. We just don't know how to solve. This is just we don't know. However, know how to round without loss given a feasible solution. of course I can start with a feasible solution all zeros, or like take some k sets, put 1, rest put 0. That's a feasible solution. Check. Take any k sets, substitute and take any k sets, set those xi equal to 1, set everything is 0. So of course I know how to find a feasible solution. But that feasible solution, if you do some ILP business, it will give you how much those k sets can cover, only that much, right? So we know how to round without loss given a feasible solution. So third, if we get good feasible solution, okay, if we get good feasible solution, then we are happy. Now notice we are not going to lose in rounding, right? So the algorithm has a following step. Find a feasible solution, find a good feasible solution to non-linear programming 2, right, and round and get ILP solution. Okay, and this rounding is called Pipage rounding. Okay. Now notice, because in this rounding there is 0 loss, right? So where will we lose? Here. Okay. So if I can say, if I can show that, hey, I have found your solution here. If I can show that, hey, I have found your solution, this is maximization problem, right? So I said, hey, I have given you some solution x star such that its value is at least opt by alpha or opt by some constant c. If I can give this, then what am I returning here? What will I will return an x integral with value how much? At least opt by c. So what is the ratio of this approximation algorithm? See, right? So it is all about how good we are able to find this. Is that correct? Right? So this is a prototype of an algorithm using Pipage rounding. So we go to a program, which is like, these are basically convex programming and this and that, whatever it is called. We don't know how to solve, but using some sister functions or sister this thing, we find a feasible solution, and then there's a normal Pipage rounding that we will learn that rounds up to this. Okay, is that fine?
There will be no loss in this.
No, you will see. I will do a Pipage rounding in a minute. Okay, okay. So, okay, so now let's okay. So, what is Pipage rounding gives? Given x in P, it returns an x integral in P intersection 0, 1 to m with some property. That is what Pipage rounding does. Okay. So what I'm going to say, so this is the lemma which is going to relate L and M. So now my next section is relating L and P. So I'm going to relate L and P point-wise. That P, the L is not too bad with L. Why? Because notice, if I find a feasible solution to x, that is also a feasible solution to this, right? Check. If I find a feasible solution to L of x, look at the feasible solution which optimizes L. Find that x. I have found this. That x is also feasible here. Notice, right? Summation of xj equal to k, xj is between 0, 1, and this some value is this. It's just that, what is that value? Like, is that value too bad for f of x? Like, what I mean to say is, best x star for L of x too bad for f of x optimization, or in the other sense, here of course I'm talking about LP. Okay, so x star for Lx, right? How is it too bad for f, like, or rather, like, you understand what I'm saying? Like, so suppose this is y star, right? So if I show the following thing, that give me any point for all x in polytope, if I can show to you the following, that hey, or let's say for all y in P, f of y is at least 1 by c times constant times L of y. If I show this, is this good enough for our purpose? If I show this, I think this is good enough for our purpose. If f of I is 1 by c times Ly, is this good enough for our purpose? Why? Because notice, what is my opt? Opt by c is less than equal to Ly by c. If I show this, then let's say, look at, so suppose x star is, x star optimizes L function, okay, Lx. So now let's look at this. So suppose the relation between x star and opt is okay. Okay, so what we know about opt? Opt is less than equal to L of x star. This we know. Opt of my max coverage problem. Opt ILP. Okay, is this. Now what I know here. So this is my first inequality. Now I know that if I look at function x star, this is going to give us 1 by c of f of x star is at least this much, right? Because f of y is at least, what is value of this is at least 1 by c times L of x star. What am I saying? Am I saying something correct? Okay, if I show this, what does it imply? Okay, so opt is less than equal to, let's see, opt is less than equal to L of x star, right, which is less than equal to,
It's a feasible solution.
wait,
for the
yeah,
NLP,
so this is less than equal to c times,
the NLP2.
so this is less than equal to c times f of x star, okay, right, and now we will get from here, okay, so what are we going to get from here?
F of x star is a feasible for this.
Yes, so we are going to get from here c times integral f, right, so which implies integral of f is at least opt by c, and I am good. Look at this, opt is less than equal to L of x star, and now I have shown that each value, at each value the function is 1 by c times this, which implies that I can show that c times this is upper bound on Lx star. But from this I can convert an integral solution to my this, yeah, same value. So this integral is at least how much? Opt by c, so that's 1 by c factor approximation. My, it's everything. If I do integral, I'm only going to get what? Max coverage. Everything is going to give me an integral of this, everything is going to give me a max coverage. So that is what I'm trying to show here. Okay, so if I show this, that point wise they are very much related, I will be very happy. Okay. Huh? No, I'll fix it. Okay, it's not like this. Okay. So now let's see. So let's fix the function. Okay. Oh God. Okay. So I'm going to define rho of x equal to 1 minus 1 by x to the power x. Okay. This is the function I'm going to define. Okay. This is my rho function. Now first observation is, notice, if d is less than equal to f, some d is less than equal to f, then rho of d is greater than equal to rho of f. Do you agree with this? If this is my function, then rho of d is greater than equal to rho of f. If d is some f, this is my function, and d and f are some two numbers. Okay, so here's a simple proof. D and f are some two numbers. What do you mean by domain? Yeah, so like just because you d doesn't mean domain. Okay. Yes, it is decreasing. Are you talking to yourself? Okay, so don't confuse me, right? I mean, it's not some rocket science. So let's just try to do. So what I want to show, this is greater than equal to 1 minus f, 1 minus 1 by f to the power f, right? Which same as saying as I have to show 1 minus 1 by d to the power d is less than equal to 1 minus 1 by f to the power f. Is that right? Right? So if you take log both sides, then what you will get? Basically, we have to show that d ln 1 minus 1 by d is less than equal to f ln 1 minus 1 by f, right? D is less than f, 1 minus 1 by d is less than 1 minus 1 by f. So point wise they are less, so they are done. Is that fine? I think no, or this is wrong. Okay, either you can show they are correct. It's correct. This is true. D is less than f. That's it. So this is greater than equal to this if and only if this, if and only if this, and finally I have found a condition which is true. So that's it. Okay. So now what I want to show is the following. Okay. So now what I want to show that point wise what happens is this is not something. Okay. So this is a lemma which I will not give you proof now. So what is known is that for all x in P, remember that polytope I wrote, right? So let me write it down here. So this polytope was what? X is in 0, 1 and summation xj equal to, okay, so this is a polytope I mean. For all x in P, okay, f of x is greater than equal to rho f times L of x, where what was f? If you recall, f was the number of sets an element can occur. Okay. So for all x, this is less than equal to this. Okay. I will not show this for now. Let me go do other things and come back and show this. So suppose if I show this, then I know because of whatever we argued before, if I show this, then we are done. Right? If I show this, then I am done. Modulo, I have to show you how to do the Pipage rounding. I have not told you, right? So notice, so what my algorithm will do? Suppose I have this lemma, I solve. So what will my algorithm do? Solve L of x, right? I will solve my L of x. Look at my x star, that is feasible for f. I will do Pipage rounding on x star, okay, and then output x integral, right? And as before, so this is what I will do. This is my algorithm does, okay. So now I know that, okay, so I know that opt is less than equal to L of x, right? L of x star, and so then what I can write here, right? So this is nothing but f of x divided by rho of f, right? Like you write by c or this, it doesn't matter. 1 by c is also a number, so don't get confused with that. Okay, and this is less than equal to, right, f of x integral by rho of f, right? So that implies that what we have achieved? We have achieved, right? What we have achieved? Rho of f approximation algorithm, where rho of f is 1 minus 1 minus 1 by f to the power f, right? So where rho of f is 1 minus 1 minus 1 by f to the power f. Okay, this is some maths. We will do it later. Let's do some conceptual contribution. Conceptually, what we are trying to do. Okay, but I have set it up everything. This is what you do. So in everything, you have to show that you have two things: how they are related pointwise. Okay, and if they are related pointwise, then what it implies that every point fx provides Lx provides a good estimate to this. That's all that it says. Okay. So look, you understand first of all that you might think, that hey Saket, why f of x is not equal to L of x? X is feasible, but our optimization function was very different, no? So if you compute that optimization function for the same value, Lx will give you something, fx can give you something. And I want to say how much loss is there when I go from here to there. You understand? So what is the pointwise loss? So look, so if you think what is happening, why? I mean, so L of x is one function, f of x is another function, x star is the one which optimizes this, right? But now I want to say, hey, when I feed x star, what is the value of f of x is at this point of time, right? Like how small it can be or how bad it can be. Say, hey, it is not too bad. It is at least whatever value of L of x is times this rho of f. You understand the point, right? So rho of f is like say half, right? So if rho of would have been half, I'm saying at every point, whatever Lx value is, fx is at least half of it. You understand the point? That's all that I have used here.
Okay, there's one thing. So solving of Lx, you said that we don't know how to solve Lx.
No.
I mean,
No, we know how to. We do not know how to solve f of x.
Oh, sorry. But L of x
Is nothing. L of x was.
linear optimization.
Yeah, but I wrote it the way I wrote it to prove this lemma.
Okay.
It was just written like this to prove this lemma, which I will come later. There's nothing more to it.
Solving Lx is basically solving the
That LP. That's right. Right? But the way I wrote it was also a non-integer program, right? So that I can compare here. I can use that formulation for the proof of this lemma. There's nothing more. You understand? But that is nothing but same object as this. Like point-wise they are same object. But f of x is not the same. Right? Look at the same x. You can try to see and you will see the different values coming in. So they're not. Yeah, different objective value. But I'm saying at each point, the objective value of f of x is not too bad compared to L of x. That's it. Okay.
I have a question.
Yes.
So do we use this? Have you already used this observation or?
No, we will not. We have not used it. But this observation is just to tell you that hey, like this is very obvious observation. If you think numerically, if the set size, like if the elements appear less number of times, then you get better approximation ratio. This is all that it is telling.
It's a frequency.
Yeah. So like whatever, right? So if some element appears, like if maximum number of times any element appear less than, it is mentally very clear that that will give you a better approximation when compared to when an element appears several times. Because why? Because then when you pick a sets, the number of new elements that each set covers is like much more correlated with what I have selected previously, intuitively. I'm sure you don't understand that intuition, but that's okay. Okay. So Pipage rounding, let's do the Pipage rounding stuff. Okay, so I want to do a Pipage rounding now. So Pipage rounding is not only meant for this, but it is meant for slightly more general function, and let me tell you what is those general things. And then we will show that, okay. So what is, so we want to maximize some f of x, right, over what, right? So suppose I want to maximize f of x over x in some 0 comma Okay, so this is what our objective is, right? So I want to maximize f of x here. Okay, this is what it's going to be. Okay. Okay. So now suppose the following two condition holds. This is called Pipage rounding property 1. So what is the property 1? It says for any non-integral x in P. So if you give me any non-integral x in P, what should I do able to do? Find a vector where should I find a vector Vx in 0 1 to the power m, okay, Vx in r to the power n. So for any non-integral x in P, if you give me, I can find a vector Vx in r to the power m and scalars alpha x comma beta x greater than 0, such that following property holds. What is the following property holds? Okay, such that x plus alpha x Vx and x plus x minus beta x Vx had strictly less numbered of, have strictly more integral coordinates than, have strictly more integral coordinates than x, right. So you give me any integral x in P, I will find a vector Vx in r to the power n and scalars alpha x beta x greater than 0, such that if you look at x plus alpha x Vx and x minus beta x Vx have strictly more integral coordinates than x. You understand? Is that fine? So that's my property 1. And property B is about convexity. And what it says? It basically says that for all x, f is convex in the direction of what? Convex in the direction of Vx. And since this is not very precise, like people who know, they understand this. More precisely, the function gt of x, which is defined as what? Gtx is nothing but f of x plus, let me think, t times Vx is convex over t, okay, is convex over the variable t in R, over variable t in R, okay.
So we are finding a direction along which to go so that I can make more coordinates turn.
Yeah.
Those are the directions.
Okay. So do you know what convex functions are, right? Okay. So basically, convex function mean that, like, you have two distinct point x and y, x not equal to y, and you choose some theta between 0 and 1, right? So then it is basically, it says that x plus 1 minus theta y is convex, right? So this is less than equal to theta times gt of x plus 1 minus theta times gt of y. That's it. So this is what convexity means. Huh? X not equal to y. Huh?
Theta x or only x?
Oh, sorry. Okay, is that fine? So suppose my function satisfy these two inequality, these two constraints. Let's say why we can do Pipage rounding A, and then we will show why our f of x satisfy these two conditions. Okay. Okay. So I have, okay. Okay. So what I want to show, okay, so this is a theorem I want to prove. If PA and PB are satisfied, then what can I say? Okay, if PA and PB are satisfied, then given any x in my polytope, any x in P means feasible solution, there exists an efficient algorithm to compute what? Efficient algorithm, let's say Pipage. I don't know why it is called Pipage, but it is called Pipage. Okay, algorithm Pipage, which returns x integral, I think, okay, in P intersection 0 comma 1 to, this is not, it is 0 comma 1 to the power n, okay, it is not 0 comma 1 to the power n, okay. So please distinguish, it is 0 comma 1 and this is curly bracket, yes, okay, with what is the property? F x integral is greater than or equal to f x, right. So value of this is this, and this is an obvious algorithm. So let me write down this obvious algorithm, okay. So this is my Pipage algorithm, okay. So look, I'm going to use this property, like it has PA and PB, everything, right. Why we can find these things for, okay. So this is Pipage procedure rounding, okay. So what I will do, while, what should I do? While x is not in 0, 1 to m, we will do the following. So what I will do, okay, I will first use PA to obtain what? To obtain Vx, alpha x and beta x. Three things I do, okay. If f of x plus alpha x Vx is greater than or equal to f of x, what should I do? What will I do? Then x will become x plus alpha x Vx, okay. Else I will set x equal to x minus beta x Vx. Done. This is my end of my algorithm. You understand? This is it. This is my, why this works? We will see, okay. And I have not proved this lemma for you people yet. That is for the approximation factor, that is nothing to do with the, okay. So what my algorithm is doing, if you notice, okay. So first of all, yes, hi Tanmay.
So in property A, we should also be able to find these Vx, alpha x, beta x in polynomial time, right?
Yeah, there is an if, suppose like, yeah, such that, okay, sure, of course, otherwise, yeah, in polynomial time. Find a vector this and scalar this such that this happens, okay, and of course in p time. You are right, or whatever time it takes, then it will give you corresponding running time.
Right.
Okay, so this is why. So for example, even if you find this in quasi polynomial time, it's perfectly fine. So first of all, notice that how many times this loop will run, m time, right? Because each time we are increasing number of ones, like number of integral coordinates by at least one, right? Use PA to this, like every time we will show this, that the number of each PA to obtain this and this and this, okay. But now what is not clear to us, okay, why will this value increases in one of them, right? Why?
You mean one of them, for one of them it has strictly more integral part, or
Both, such that this and this have strictly more integral. Did I write?
But in that while loop, you're writing while x is a 0, 1 vector
Okay, fine. So now let's, so we will first of all, like you might ask, right? So what is this tells us? That you give me this, I will give you a vector. So every time I'm going to apply this, right? And every time I'm going to go to a vector which had strictly more, right? Such that this had a strictly more integral coordinate, a strictly, right? So every time number of integral coordinates increases, right? So if we can ensure that, hey, either this, so what I'm going to show that max of x plus alpha x vx comma f of x minus beta x vx is greater than equal to f of x. Yes, that's all that I'm trying to show.
So this means that property of finding those things with those specifications will automatically give you a better.
Yeah. So that PA first allows, and now this is where I'm going to use the fact that f is a convex function. Okay, but give me a minute. Okay. Okay. Give me like. One second, sir. Don't, please. Let me think. Yeah, tell me what you want to ask.
So that if condition, should not it be strict?
Which one?
If x plus, like after the translation,
No.
should be greater than f of x.
No,
You update.
greater than equal to.
If it remains equal, then why?
What does that matter?
At least integral.
In number of integral coordinates increases, right?
At least that, yeah.
That's why I'm doing only M loop. It is not about that the value which I'm only just trying to increase the number of integral coordinates. One second. Don't let me think. Otherwise, I will get confused. So give me a minute. Alpha x, beta x, alpha x plus. Okay, it's the same thing. Plus minus beta x alpha x. Is this fine? See, this is equal to 0 because what is this? This is alpha x beta x, this is minus beta x alpha x. So top is 0, so this is 0. Right? Is this fine? Okay. So now I want to apply g on this function. G. Okay. So we know that this is a convex function, right? Over variable t in R, this is theta times this and this, right? So what is my theta and what is 1 minus theta here? So look, this is alpha x. What?
This fractional part should be theta and 1 minus.
This is my.
But where is your x? Shouldn't x show up somewhere?
This is my x.
This is x.
That is alpha x.
But that is my x.
Scalar.
Works as this x.
What?
Say for the
Why
convex
will it not
function,
work for?
you
Will
need the two vectors x and y.
why? Why they
Finding
can?
the points.
What
Alpha
point?
x and beta x are scalars.
Where it told alpha x and beta x are scalar. So what?
But the
This is a point, no?
it's a point. It's not a point. The argument passing through G should be a point. What you
It's
have,
over variable t in R.
okay, but the theta x plus 1 minus theta y, that's representing a point, meaning it should have m coordinates. And x itself is a point and y scaled by theta and 1 minus theta respectively. Over there what you have is just a scalar 0. I'm saying you're not passing the correct argument.
Okay, maybe did I make a mistake? Look, Shushmita, what is my GT of x is? F of x plus tvx.
That's fine, but
Wait,
x is a point,
wait.
m coordinate point.
Yeah, I understand that.
So, but that's
Wait,
okay.
let me complete now. So GT of x is this point,
Okay.
right? So I'm trying to understand what is GT of 0.
But 0 is
Wait,
is 0.
Zeta of 0 is nothing but f of x plus 0 times vx. This is what we are talking about.
But second, 0 is not a point. Like 0 is just one value 0. That x you're passing through the gt function, it has to be a point. Like it has to have m coordinates.
Where? T is an element of R.
That's fine, but x
Okay,
the
I shouldn't-
argument you're passing through gt.
Let's put it this. This is how I define.
What is the relationship of x then?
X is f of x plus tvx, right? So if you give me a 2 point, I will do this. So okay, this is. Okay, so let's see.
I think what you want gt to be is to be the scalar closure, this convex closure of the set function. So it has to have a relationship with
Wait, Shushmita. This is what my function is. G of xt is this. Okay. Yeah, so in this direction, so this is what it is. Fine. Okay. So now, what is this going to be? GT of x is going to be, so basically, what is this my point t is? Point t is 0, right? This is what it is, right? So now, what am I going to get here? You tell me. I understand that, but I have written my 0 as these two things, right? And this is a function which is a linear combination of, if in t, it's a linear. So what is the meaning that linear combination of t it will be? Please tell me. If I can write some t1 into this, then I will write it like this. So if I write g of x times, say, theta times t1 plus 1 minus theta times t2, what it will be? Please tell me what it is, right? Then because it is a convex in this, I can write it, right? Theta times g of x times t1 plus 1 minus theta times g of x times t2. This is what I am trying to say, right? So think of this as like theta, then what is this? Minus theta. Huh?
that is 1 minus theta.
That's it, right? So because of this, what will I write here, right? So
And alpha x is behaving as t1 and beta x
as behaving as t2. Okay, so this is like a t1 and this is like a t2, right? Now check. Is that fine? Okay, so now what will I get from here? So this is equal to, if my understanding is correct, this will come out. So this is less than equal to beta x by alpha x plus beta x, and what is this? This is
gx of alpha x.
g of x of alpha x, what is what? Which is f of x plus alpha times vx, which is f of x plus alpha x vx. And if I take out this common, what will I get? Alpha x by alpha x plus beta x, and what is this minus beta x? Right? Of minus beta x. This is I am going to get f of x minus vx, which is what I was interested in, right? This is what I was interested in, and this is what I was f of x minus beta x beta vx I was interested in. Is that fine? Okay. So now, what is beta x alpha plus beta x, and what is this quantity? Both are greater than or equal to 0, because alpha x beta x is strictly greater than 0. So this is strictly greater than 0, this is strictly greater than 0. Okay, so if both are strictly greater than 0, is it possible that this is also less than gx0 and this is also less than? what is gx of 0? So gx of 0, right? Is it possible that this quantity is also less than gx of 0 and this quantity is also less than gx of 0? Is it possible?
Okay, gx of 0 is at most this.
Imagine, okay, wait. Suppose this is what I wanted to show, right? This is what I wanted to show. Okay, suppose this quantity is also, suppose this quantity is greater than or equal to gx of 0, and this quantity is also greater than, sorry, strictly less than g of x 0, strictly less than gx of 0. Then what am I getting? Then I am not getting that this is strictly less than 0, which is contradiction, right? Because gx of 0 is less than this, and then you are saying that this is less than this. This is not possible, which implies that g of x 0 is less than at least one of these two quantity. But what is g of x of 0? Is nothing but f of x, right? What is f of x? This is same as gx of 0, right? Because if I substitute 0 here, I will get f of x, right? So I have shown this. That's it. There is nothing more to it. Okay. So this is what Pipage rounding does. Okay. Oh my God, I have killed so much time. It's 110. Okay. Okay. Let's try to. So this is fine, right? So if my function satisfies this quantity, if my function satisfies this quantity, then for sure I can show that my Pipage rounding algorithm has a property that after every rounds, number of integral coordinates increases and the function value never decreases. Is that fine? Okay. Now there are two things. First, why is this lemma correct? That's one. And secondly, why is our vector correct for this? Okay. Do you have a class today at 2? Who has, anybody has class? I need half an hour. Huh? You have a meeting.
But I think I can change that.
What's this? Like 110. Can we meet in 20 minutes? Everyone, I want break. I want break. I'm hungry somehow. Pallavi, do you have a class today?
I'll not be going for that.
Huh?
No, I'll not be going for that.
Like, oh, you're not teaching a class
We
today?
can, I'll not teaching.
Okay. Can we meet at 1:45? Because if I leave it now, it will be dead for all of us. Like, this is not something which I can just leave it and go away.
Would also be there.
Yeah, because otherwise I will have to repeat everything, and that I do not want. Okay. It's like we are almost close to what we want. Tanmay, is it okay with you? Hey.
Yeah.
Okay.